Hi everyone, welcome back to our channel. Today we are going to do the MATLAB simulation of verification of KCL for a bridge T network. Here you can see here, so this is an T network and this is have a bridge with an element of 1000 ohms. Okay, so we have to construct this bridge T network in simulation, and we have to prove that the KCL is verified at node 1 and KCL is verified at node 2. So here you are not going to get a new node. Why? Because the voltage at this point is 30 volts. Let's try to see this circuit once and later we will design the same. Here you can see here the current which is leaving is minus 6.73. Current which is leaving is 6.15 milliampere. Current which is leaving is minus 9.231. Okay, so if you add all this current, so it's nothing but leaving currents are minus 6.9 plus 16 minus 9. Okay, so minus 6 and minus 9 which is equal to plus 16, automatically that both will get cancelled out. Automatically KCL is verified at this node. But coming to this node, the entering current is equal to leaving current. This is the entering current and this is the leaving current. How I'm saying it's entering current is this is positive and this is negative. That's how the current is entering. Here the current is leaving. Why? Because this is positive and negative. Why? Because this is positive and negative. So entering current is minus 9.231. So that is equal to minus 4.615 milliamperes minus 4.6 minus 4.6 minus 4.6, which is equal to minus 9. I can say that entering current is equal to leaving current. Therefore, KCL, Kirchhoff's current law, is also verified at node 2 and it is also verified at node 1. This is how to verify KCL using MATLAB simulation. This is an MATLAB how we can practically verify. Okay, so in order to demonstrate you, I am showing that I added all the leaving currents and I had got the value as 0. Here also entering current is equal to leaving currents, that value is equal to 0. E to the power minus 15 is indirectly 0. Okay, now let us try to do the same thing in our simulation. So in order to perform the simulation, first what I have to do is so here you are going to have the MATLAB. Okay, so this is R 2018B MATLAB version. So in this version, here you have at the top Simulink. Click on the Simulink. As soon as you click on the Simulink, you have an blank model. Click on the blank model. You click on this blank model, then it is going to open a window like this. Okay, so when you got a window like this, now let us try to move this untitled Simulink to the right side, and let's try to keep what actually we need to design in the left hand side. Okay, so now we're trying to keep it in the left hand side. So this is actually what we have to design. Let's try to identify the components what actually we are having. Okay, so when you come to this original components, so you have a voltage source and an ammeter and a resistance, and here we require to measure the current in all the branches. So we require all the ammeters. The resistive branches are 2000, 1000, 1000 and 1000. Okay, and with a voltage source at both the sides. Okay, so the same we are going to first insert the elements and we are going to give the connections. In order to search the elements, here you have the library browser. Click on the library browser, and in this library browser, here you can see here, scroll the cursor down, and here you're going to see here Simscape. Click on the Simscape. Under the Simscape, come to the block called as electrical. Under this electrical, come to the next subsystem, which is nothing but specialized subsystem. Under this specialized subsystem, you're going to have an fundamental blocks. Click on the fundamental blocks. In order to run this voltmeter and ammeter, we require an power GUI. First drag the power GUI and then go to electrical sources. In these electrical sources, we require an DC voltage source and drag the DC voltage source. And the next element we require an resistive branches, just drag the series RLC branches. And the interfacing, this voltage and current we don't want, and we require the measurement of voltage as well as current. So we require only the current. Let's try to keep the ammeter. Okay, Now let's try to give this connection. Let's try to verify is anything missing. Okay, so voltage source is there, ammeters are there, resistance are there. That's all. Okay, so depending upon the circuit, we'll try to give the connections. Okay, so enlarge this system. So in each block, first let's try to construct the original circuit and then you'll inject. So double click on this element and label the branch type as R, click on apply as well as OK. And the first series branch, here you are going to get it as 2000 ohms. Just keep it as 2000 ohm. And one more series branch is there. Just copy this branch and paste the branch here. Okay, and the value of this resistor is 1000 ohm. So enter the value of 1000 here, click on apply as well as OK button. Okay, so after this you are having a shunt branch. Copy this branch as Ctrl C and paste the branch as Ctrl V and click on this branch and use the rotate Ctrl R, automatically it will be rotated. So we had a bridged element and we require one more element. So copy this element as Ctrl C and paste the element as Ctrl R and just rotate Ctrl R button, you get in vertical. And you require one more voltage source. Copy this voltage source and paste this voltage source. Now we require the current in all the branches, and at the top also you have one more resistance. So copy this resistor and paste here. Okay, so this is a bridged network. Okay, now we have to inject the ammeters also in each branch. Now to identify the, let's try to see the original simulation how we are having. Okay, so in this branch we require one ammeter, in this branch you require one more ammeter, in this branch you require one more ammeter, like this. Okay, so and you can identify the elements values are 2000, 1000, 1000, 1000. So this is only 2000, remaining are 1000. Okay, so let's try to give those values. So the value of this resistor is 2000 ohm resistor. The value of this resistor is also 1000 ohm resistor. Just click on apply OK button. And coming to this branch, this is also an 1000 ohm resistor and this is also an 1000 ohm resistor, and the voltage source of this source is with a magnitude of 30 volts. Click on apply and OK. The magnitude of this voltage source is also 30. Apply on apply and OK button. And coming to this bridge T network, the value of this resistor is also 1000. Now let's try to connect the ammeters. Okay, so connect the ammeter in this direction. So this is the branch. Let's try to connect the ammeter here. So and in this branch we require the current. So let's try to paste those ammeter. Copy the ammeter and paste the ammeter. So the current which flows in this branch also we require. Let us try to place the ammeter. So if you have any doubt, you can check it out where to place. So this is 1 ammeter, and here also you'll be getting one more ammeter, and we need to have one more ammeter in this direction. Now let's try to give the connections via ammeter. So let's try to take this is the entering current. Okay, just try to rotate using Control R button. Why? Because this will be an highest potential, this will an low potential. From negative connect to the voltage source, from positive connect to this resistor, and from this you connect to this resistor, and the current will be flowing down. Just rotate it as Control R and connect the positive of this to the network and negative to the resistance and negative of this to the voltage source. And from this you connect to positive here, and here the current will be leaving, which is not, just rotate it and connect the ammeter here, and from the negative connect to the positive of the ammeter, and from negative connect to this resistor and from this resistor connect to this voltage source, and from this voltage source just short circuit it, and here the current will be flowing, and current flows in this direction. Why? Because this is a high potential. Just rotate it, and this will be connected to the positive terminal, and this will be connected to the negative terminal, and this outer resistor will be connected to this branch, where this will act as an continuous. Now if you want, you can define the values. All are now very clear. So this is of 30 volts, and this is also of 30 volts, and you want to, if you want, so I'm taking this as a reference. Therefore current is leaving in this direction, current is leaving in this direction, current is leaving this direction. For this node, current is entering, current is leaving, current is leaving. Just we need to verify. Let's try to keep the uh, displays. Okay, so in order to have the displays, click on the browser and come to sinks. In this sink, just use the display. You'll get the current in ampere, but it is very tough to understand in ampere. Let's try to go with milliamperes. That's why you require a multiplier. Come to commonly used block. Here you are going to have the gain. Just take the gain, and now we'll inject in each element. Okay, in each branch. Okay, so this value of current is multiplied with 1000. Okay, that's why I'm writing here this as 1000, and just click on apply. Okay, whenever it is multiplied with 1000, and the resultant answer will be in, so this current will be in milliamperes. So I1 in milliamperes. Similarly, I want the current in this branch. Just copy this one and place it here, and copy the gain also. So copy the gain of 1000 and place it here, and next again also copy this value and paste it here, and here you are going to have the gain. Just keep the gain here. So output of the ammeter connect to the this one, and just run it. Let us try to test whether it is working or not. So just run it. As soon as you run it, you are getting the currents, and these currents are in milliamperes. Okay, and you can see here, when you find this, the leaving current is, I mean, all the currents are leaving. So therefore 0 is equal to minus 6.9 plus 16.15 minus 9.23. So when you get this value, and you can see here, let us try to do with an calculator, then you can understand well. So there is no entering currents, all are leaving currents. Therefore 0 is equal to minus 6.925 plus 16.15 minus 9.23, which is equal to plus 16.15 minus 16.15. Therefore entering current is 0 ampere, leaving current is also 0 ampere. Therefore the KVL is verified at this node 1. Okay, so node 1 KVL is verified. At this node, KVL is verified. So here you can see here, all are leaving. This is also leaving. This is also leaving. This is also leaving. So leavings are minus 6.23 plus 16 minus 2.3. Automatically it is balanced. When we come to this node, let's try to do the KVL at node 2 also. So at node 2, what's happening is, so this current is entering current is minus 9.23, leaving current is minus 4.6 and minus 4.6. Minus 4.6 and minus 4.6 is minus 9.2. So entering currents is equal to leaving currents. Okay, so this is what you are getting when you apply the nodal. I mean, it's nothing but the nodal is nothing but applying KCL at node 2. So at KCL at node 2 also, entering currents is 9.2, leaving currents is also minus 9.2. Therefore, KVL is also verified at node 2. Okay. So this is how to do the simulation. Okay. So simulation is nothing but the verification of your calculation. So whether you have done correctly or not, or any mistake is there, you can verify through this simulation. Hope you are able to understand the simulation. So very simple. 0 is equal to all are leaving, all the currents are leaving, and here entering current is equal to leaving currents. This is how we have been verified. Okay. So hope you have been understand clearly the concept. If you feel the explanation is good and it is easy to implement, give a like to the video and share to your friends those who are studying this subject and simulation. And if you have any doubts, let me know in comment section. And if you're watching my channel for the first time, subscribe to my channel with the name KV Tulasi at the rate EV Crush, and kindly encourage this sort of free channels for the development of students and faculty. Thank you for watching. We'll meet in an next upcoming video on verification of KVL. Yours, Ram.